Chapter 7, Atmospheric Pressure and Wind. 7.2, Wind. Wind can be defined simply as air in motion. The reason why we can feel wind is because air has mass. Even though it's composed of mainly gas molecules, those molecules exert force when they strike an object like our bodies. The faster the winds flow, the stronger we feel it. Wind can be in any direction, east, west, north, south. It can also be up and down. However, the horizontal component of wind flow often greatly exceeds the flow that occurs vertically. Now, there are some exceptions. Thunderstorms can produce strong vertical blasts that move towards the ground surface. Wind develops as a result of spatial differences in atmospheric pressure. And one of the main factors responsible for differences in atmospheric pressure across the Earth's surface is differences in the absorption of solar radiation. Globally, we should expect winds to blow from the poles to the equator. And that's because the poles receive very little solar radiation, while the equator receives quite a lot and warms up a lot more than the polar regions of our planet. Wind speed tends to be greatest during the daytime. In particular, it's usually greatest in the afternoon. And this is when you have the greatest spatial extremes in atmospheric temperature and pressure. With sunset, you'll see that winds slow down and become almost non-existent during the night. Surface wind speeds tend to be faster over the oceans and slower over the land. They're faster over the oceans because there's less friction. Over land, buildings, trees, mountains slow down winds. So here we have a simple model showing the formation of wind. And we can see wind blows from high pressure to low pressure. In this model, we see the clouds are keeping the area to the left cold. This creates descending high pressure air, dense. On the right, the sun is warming up that surface, causing the air above it to heat up and to rise, forming a low pressure system. Wind is often described by two characteristics: wind speed and wind direction. Wind speed is commonly measured by an anemometer in kilometers per hour, miles per hour, knots, or meters per second. Direction is measured by an instrument called a wind vane. Both of these instruments are positioned at a standard distance of 10 meters above the ground surface. In this image, we see the two instruments used to measure wind speed on the right and wind direction on the left. Here are the common directions used for measuring wind direction. Notice when we talk about a north wind, we're saying it's coming from the north. If the wind is a west wind, it's coming from the west. The major wind directions are north, northeast, east, southeast, south, southwest, west, and northwest. In between, we have some minor directions. Now, winds blow according to Newton's laws of motion. So they're influenced by these laws. The first law of motion suggests an object in motion will stay in motion as long as no opposing force is put on the object. Now, this can be easily illustrated with Canada's favorite sport, hockey. One of the reasons why it's played on ice is because ice has very little friction. So when the puck is shot with the stick along the ice, it continues at a high velocity. It doesn't seem to slow down. If hockey was played on a sand surface, the puck wouldn't go very far, because sand would have a great frictional effect. The second law of motion suggests the force put on an object equals its mass multiplied by the acceleration it achieves. So we can write this down in two equations. So force is equal to mass times acceleration. Or more importantly, the bottom equation is the one that we think of the most, that the acceleration of a mass is a function of its force and its size, its mass. So for example, the more force you put on a puck, the harder you hit it, the faster it's going to move or accelerate. If you make the puck larger, more massive, and use the same amount of force, it's not going to accelerate as fast. The primary force responsible for wind is called pressure gradient force. Horizontally, at the surface, wind always blows from areas of high pressure to areas of low pressure. Vertically, winds move from areas of low pressure to high pressure, so it's the opposite. The speed of a wind is determined by the rate of air pressure change between the pressure centers. Now, to express this scientifically, we use this concept of pressure gradient force. And pressure gradient force suggests that wind is influenced by a force that's determined by the pressure change over a unit distance. The greater this force, the faster the winds will blow. This diagram here illustrates pressure gradient force graphically. Pressure gradient force should be strongest in the top left-hand corner, where it says fast and the thick arrow. The isobars indicate to us that the slope or the pressure gradient here is very, very sharp per unit distance. The winds blow slowly from the center of the high to the bottom right-hand corner. And the reason why they blow slowly here is because the pressure gradient is much shallower. The second law of motion suggests that the force put on an object equals its mass multiplied by the acceleration produced. Pressure gradient force is the primary force influencing the formation of wind from local to global scales. And this force and the resulting winds are determined by the spatial pattern of atmospheric pressure at any given moment in time. Let's look at a figure that illustrates how pressure gradient force works. And we're going to have two different pressure gradient scenarios, and we'll see that this influences relative wind speed. On the left, we have a 10 millibar change over a 100 kilometer unit distance. The resulting pressure gradient force could be calculated out simply as the pressure change divided by the distance traveled, or 0.1 millibars per kilometer. In the right-hand diagram, we have the same distance traveled, 100 kilometers, but now our pressure changes 40 millibars. So to calculate pressure gradient force, 40 divided by 100 equals 0.4 millibars per kilometer. Now this number is 4 times greater than the number that we calculated on the left. Therefore, wind speed will be 4 times greater. The rotation of the spherical shaped Earth creates the second force that can act on wind. We call this Coriolis effect or Coriolis force. Newton's first law of motion suggests air will remain moving in a straight line unless it is influenced by an unbalancing force. In this case, the unbalancing force is caused by the spinning of the Earth. The consequence of Coriolis effect on wind is that the moving air changes direction. Instead of the wind blowing directly from high to low pressure, the rotation of the Earth causes wind to be deflected off course. In the northern hemisphere, wind is deflected to the right of its path. In the southern hemisphere, wind is deflected to the left, opposite of the northern hemisphere. The magnitude of Coriolis effect varies with the velocity of the wind and the latitude at which it's blowing. Coriolis effect only influences wind direction and never wind speed. There is no change in wind speed. The following diagrams illustrate Coriolis effect. So let's begin with the diagram on the right top. So we can see the Earth rotation from the North Pole. It's counterclockwise. The yellow dotted line represents where the wind wanted to go. Now the Earth is spinning underneath the flowing air. And what happens is the real path that the wind takes is deflected because the Earth has moved underneath the wind. So the green line represents, or the green arrow represents the actual path of the winds. The reason why deflection is opposite in the southern hemisphere is because from the South Pole, the Earth's rotation is actually clockwise. So here we see the yellow line represents the intended path. The green line represents the path actually taken. The diagram on the left also illustrates deflection. Notice in the northern hemisphere, it's to the right. And in the southern hemisphere, it's to the left. There is no Coriolis effect at the equator, and that's what's illustrated in this graph. So this graph shows winds of 3 different speeds, 5 meters per second, 10 meters per second, and 20 meters per second. And the amount of Coriolis effect in meters per second squared on the y-axis. So in the x, we can see latitude, and we can see that the amount of Coriolis effect increases with latitude. And it doesn't matter what the speed of the wind is, except that if you double the wind of the speed, if you double the speed of the wind, you double the Coriolis effect. So if we move from 5 to 10, there's a doubling of the effect. And if we move from 10 to 20, another doubling of the effect. Here's another image showing us the Earth rotation, the intended path being the black line, black dotted line, and then the actual path, which is the yellow line. So the top represents the northern hemisphere, so deflection is to the right. The bottom diagram is for the southern hemisphere, and the deflection is to the left. Here we have another diagram showing the amount of deviation as a function of latitude. So we can see if the plane flies along the equator, there is no deflection. It travels straight along the line of the equator. At about 30 degrees latitude, the deviation is smaller than the deviation that would occur at 60 degrees of latitude. The final force that can act on wind is friction. Now, friction can only exert a force if the air is actually in motion. And friction as a force operates in a direction opposite to the path of the motion of the wind, which is being caused by pressure gradient force. The effect of friction is a drag. It causes the wind to decelerate. Obstacles on the Earth's surface cause friction. And for this reason, frictional effects on wind are limited to about 1 kilometer above the Earth's surface. Above 1 kilometer, winds blow in a virtual frictionless environment.